can make from scratch. Okay, so what did we do last time? Did you sign up for a ham exam? If you haven't gotten confirmation from Sharon, like an email telling you what time to come, you have to register again. Or if that doesn't work, then please send me an email and I'll register you manually, okay, with all the information. Okay, last time we talked about discrete time processing of continuous time signals. We also talked about continuous time processing of discrete time signals, which sounded kind of weird, but at the same time, if you think about this, this is a really useful tool to understand what operations we do when we do any operations that we do in discrete time that maybe is not easily described. If we consider the signal to be basically a continuous time, then we're able to understand how the system actually works. Then we went over downsampling, and what we're going to do today is we're going to continue on and go for keeping the topic on changing the sampling rate via digital signal processing. We'll go over upsampling. Then what happens if you want to do some arbitrary rational resampling of your signal? And you want to do that basically if you have different sampling different sampling rates of different systems. You want to adjust them. It's very, very common that you have, for example, certain variations in clocks between two systems, and you want to be able to compensate for them. So you have to resample, okay, in order to compare two signals. We'll see that this could be really expensive. So at the same time, what we're going to do is I'm going to show you, we're going to start talking about interchanging operations that would lead to a polyphase decomposition and a multirate, which will allow you to do all these things faster. Okay, but that will be on Friday. Okay, just to review, what is downsampling? So downsampling, you can think of it much like a continuous to digital conversion, where you, in fact, if you have a very finely sampled signal, it's like a continuous signal. When you downsample it, it's really like sampling it. Okay, so if I have something that's really, really fine and I downsample it, then it's really much like sampling. So we should see the same effect as aliasing, and we need to mitigate with this aliasing by using so-called anti-aliasing filters. We showed last time that if you have a decimation operation, that gives you, in fact, a replication. I mean, it kind of makes sense, right? Because sampling of a continuous time signal gives you replication of the spectrum. Now we're in the discrete domain, but we're downsampling. If we downsample by a factor of 2, then we should see kind of a replication of 2, right? But the Fourier transform only goes from minus pi to pi. So these two replicas should appear within the same range. So what we do get is we get scaling and replication. Okay, for that to fit. Okay, so the effect of downsampling is a scaling by a factor of the downsampling factor, and then replication of the scaled signal the same amount of times as the factor, which, as I showed you, is really comes down to take a replica and stretch it. Okay, and take its the second one and also stretch it, and that will give you basically now something that was from minus pi to pi, minus pi over 2 to pi over 2. Now it will show up from minus pi to pi. Okay, and it kind of makes sense because if we had a continuous time signal and we sampled at a particular rate that was twice the Nyquist rate, okay, not twice the highest frequency, twice the Nyquist rate, we'll have kind of empty spectrum, okay, around it. If we then, instead of that, sample at a Nyquist rate, then we should have a spectrum that will only have the triangle from minus pi to pi. So if we do sampling at twice the Nyquist rate and then downsample by a factor of 2, we should get exactly the same thing. Okay, if that makes sense. Now, if you sample by a factor of 3, now it doesn't fit within the spectrum, so you get aliasing. Okay, that's the usual behavior. Okay. How do we mitigate with aliasing? What? Anti-aliasing filter. That's right. So if we have a spectrum and we want to undersample it by 3 or downsample it by 3, we perform an anti-aliasing filtering and then downsample, which will give us this. And that will be exactly the same as if we did an anti-aliasing filter for a rate, the original rate that was 3 times slower, and then downsample at that rate. Okay? So if originally would have aimed for a lower sampling rate by a factor of 3, we should have gotten the same spectrum if we use the right anti-aliasing filters. Okay, so we can do sampling in kind of 2 stages. One, sample above the Nyquist rate, and then in digital, downsample it to the Nyquist rate, or even with anti-aliasing filter below that. Okay. So the nice thing that allows you to do things also in the digital domain, and you'll see that it comes to be very handy, especially because anti-aliasing filters are not perfect. So if we oversample, we might be able to correct for some of the non-ideal behavior of these analog filters. Okay, and I'll show you that later. Any questions up to here before we move to upsampling? It's all clear. Midterms are out. Scores are out. I was kind of surprised. That was the distribution. So I guess everybody should, like, if basically, it should have been something like this, right? Where this is perfect. It's never a Gaussian. So when people say that, a class should be bell-shaped curve, it cannot be possibly bell-shaped curve, because in that case, you might have negative scores and also scores above the maximum score. So it's really not bell-shaped. I was actually pretty happy, I think, from the result. The results are, a lot of people did really well, and those that did not do really well didn't do that bad. So, and it wasn't an easy exam. So I think you did really well. So go like this if you did well. Okay. So what is upsampling? Much like downsampling is sampling, okay? So continuous to digital conversion, similar. Then upsampling is very much like digital to continuous conversion, okay? Because we're going to have now a finer rate. If you think about this, what does a digital to continuous time domain does? Okay, let's say I have a certain signal and I am able to resample it so it's much faster. So I have sampling like this, and then I produce something which is finer. Is that continuous? No. But what if it was like, gives you finer and finer samples? Okay, is that continuous? No, but at the end, if I really, at an atomic level of sampling, then it would be almost continuous, right? So if you think about this, this is very, very similar. So now recall that our discrete to continuous time model was that you start with something that is sampled. Then we went to X sub S of t, which is the impulsive version of it. Then we filter that into a continuous time signal. Okay? What we're going to do now is something very similar. We're going to approximate X sub S of t by placing zeros between samples. So it's kind of like an impulsive, if you think about this. And then we're going to convolve it with a sinc, which is a band-limited interpolation. Okay, so we're going to do a similar operation, only we are not going to go for the continuous time. But ideally, the model that we're going to use is that our signal comes from a band-limited class of signals. So we could have interpolated it to the continuous domain and then resample it at a different rate. Right? That's in the back of our minds, we're thinking about that. This is exactly what we're doing. But we never go to that domain. We always operate on the discrete samples. Okay? We don't need to go to the continuous time because once we sample a band-limited signal, we know everything that needs to know about that signal. The samples represent everything, all the information. Nothing is lost if it's band-limited and we sample at or above the Nyquist rate. Okay? So that's why we are able to do all these operations, the resampling, downsampling, everything. We could do that in the digital domain because all the information is there. So here's how we do it. Okay? We start, so originally we had x of n, which are samples at a rate of a t sample interval. Okay? We sample at a particular rate. So x of n is really the evaluation of our continuous time signal at times n times t, where n is an integer. What is the interpolation? Like, what does resampling means? We want to achieve from resampling is as if we sampled at a higher rate. Okay? That's what resampling means. As if we sampled at a higher rate. So our interpolated signal should have been x sub c evaluated at n times t prime, where t prime is some faster multiple of this t period. Okay? For example, if L equals 2, then we would have sampled it twice as high of a rate. Okay? So we want to obtain x sub I, the interpolated signal, from x of n, as long as it was Nyquist sampled, in these two steps. What we're going to do first is generate this x sub s. But it's not x sub s because it's discrete. We're going to generate x sub e, which looks like x sub s, but it's discrete. Okay? And what x sub e means is that we're going to place zeros in between our samples. So we took something and we created this impulse, like a virtually or discretely impulsive signal. Now this is an example for L equal 2. If we wanted to do L equal 3, we would have put 2 zeros. L equal 4, we would put 3 zeros. Okay? All right. So we're going to put zeros, and this basically says that only when you've got n equals multiple of L, you've got some samples, and otherwise it's 0. So this basically expression just tells you, hey, stretch it. This is called an expander. Okay? It expands the signal, puts zeros in between. Okay? Very simple operation. Is it translation invariant? Is it? Is it translation invariant? Is it? If you have a shifted input, do you have a shifted output? No, it will shift by 2, right? If I shift this by 1, this will shift by 2. Okay, so it's not translation invariant. Okay? Is it memoryless? No. Okay? Does it make it hard? What's hard? Okay. So now what we're going to do, the second stage, we're going to take this x sub e, and we're going to low-pass filter it. Okay? I mean, we create this impulsive signal, right? Now we're going to low-pass filter it using a sinc interpolation. So for every sample, we're going to place a sinc in a very similar way that we did from from digital to continuous time. But now, I mean, if we wanted to go to continuous from discrete to continuous time, we would have did a sync interpolation, right? And then just play the continuous signal. But now we want to evaluate at twice the rate. So we're kind of like convolving the sync and immediately sampling at twice the rate. Okay? So we really don't need to do the full convolution. What we need to do is basically just evaluate what the value is over here and over here and over here and over here. And that's it. So it's if I did something continuous, it immediately sampled. Okay? So that's very simple. What I could do, really, is a convolution of x sub e with sync n over L. This is the evaluation of the sync. Okay? When I do that, I get samples in between. Okay? So now I've interpolated my signal. And if I... Hey, let me know if it's making these kind of noises because it's going to be in the recording. Okay? And I don't hear it as much from here. Okay, so where was it? Yeah, so if I upsampled by a factor of 1,000,000, if I upsampled by a factor of 1,000,000, then I would have had almost a continuous time signal, right? It would have followed this continuous band-limited version, right? 1 billion, upsampled by 1 billion, upsampled by 100 trillion, right? It would have been almost continuous. Okay? So it's the same thing. Okay, so formally, we start with, so the interpolated signal is really, you take the expanded signal and convolve with sync n over L. If you look at what is an expanded signal is really my original signal multiplied by shifted deltas that are spaced L from each other. Okay, L samples from each other. So if I perform this convolution, then effectively I have sinks that are spaced integers L from each other that I evaluate them at those points, okay, where each of the sync coefficients is the original signal. Okay, so shifted, scaled, sinks evaluated at twice the rate. Okay. Any questions? This is actually really how it's done. People really do this. They put zeros and then they filter. Okay, that's how it's done in practice. Do you low pass filter it with a sync? That wouldn't be that practical, right? So people approximate it when they do upsampling, and that's why when you write resample in MATLAB, it's going to do something approximate. So I want you to understand what is this approximation that's going to happen. So the frequency domain interpretation of this is the following. I've got x of n coming in. I upsample by a factor of L. I get x of e of n. And now I'm low-pass filter it with a gain of L with a frequency cutoff of pi over L to get back my interpolated signal. Okay. So if you look at what is sync n over L, is if you look at the DTFT, is really just a ideal low-pass filter, right? That goes from minus pi over L to pi over L. Okay. So if we try to understand what is the frequency response of x sub e, which is the expanded version, so we can just compute it, right? The sum from n minus infinity to infinity of x sub e of n, e minus j omega n. But the expanded signal only have values every L samples. It doesn't have values everywhere. We just expanded it. So only at L times n, you have values. Okay, so it's non-zero only for n equals ml, for some integer m. So I'm going to sum over m, a new variable, where now I'm going to have the expanded signal m times l. So this is a new variable that I'm introducing that goes from minus infinity to infinity. And now I jump every L samples. Okay? Because otherwise I would have just summed over zeros. It doesn't matter. So then this n over here also goes to m over L. So this n also is written as m times L. So this is the equation. But if I stare at it long enough, I see that this is in fact x of m. Because this is what I originally took and expanded. So what I get is the sum of x of m multiplied by this, which is x e to the j omega times L. So I get scaling, okay, or compressing of the DTFT. This is the effect of putting zeros. You get a compression of the DTFT. Compression by a factor of L. Okay? If you think about this, when we downsampled, it stretched by a factor of m, right? And then was replicated. Now we get a compression by a factor of L. No replication. Okay? So here how it looks. Let's say we start with x of c, j omega, band-limited signal with a maximum frequency omega sub n. If I sample it at a t rate, which is the Nyquist frequency, this is my x e to the j omega that I should get. Okay? Right. Now, what would happen if I sample by t prime, which is t over L? How would my spectrum look like? Yeah? Yeah, compressed, right? So if I sample by t over L, basically it's like representing from minus pi to pi, the frequency from here to here, right? So my triangle would compress and occupy only part, like 1 over L of the 2 pi range. Okay? So it's going to look like this, where this is pi over L. Now, when I do this upsampling, I'm going to take these samples, and I want to get this from these samples. I don't want to go that way. I want to go that way. I want to go counterclockwise. I don't want to go clockwise. Right? Counterclockwise. For this particular case, if I had drawn this otherwise, then I would maybe want to go clockwise. But right now, I want to go counterclockwise. It's all the reference that you have. Okay, so I'm going to expand it. Okay, I'm going to place zeros between the samples. What is that going to do? Right? It's going to compress my spectrum. So my spectrum is going to now look like compressed. Note that the height doesn't change. Okay, we just got compression from the derivation. Okay, that's not true for the downsampling. When you downsample, you do have a change in the height. Okay, so now I need to get from here to here. What do I do? Huh? I need to get from here to here. Yeah, and again, right? So, okay. So I low pass filter. Why did I draw more boxes? It has to be periodic, right? It has to be. If I'm digital, then it has to be periodic with 2 pi. Okay? So I low-pass filter by pi over L with the cutoff frequency pi over L, and then I get this. Ta-da! That's it. So now I really didn't have to go through the continuous, but I remember in the back of my head that this is really the signal that I'm interpolating using that way. Okay? Any questions? Yeah.
Is this a causal link? So the sync is non-causal. Can we like give up a bit in the low pass filter? Maybe like the phase. Causal link.
Sync is not causal, right?
Yeah.
What you could do is use a non-ideal filter that is causal. What it would cause, though? You will have to have some delay, right? So if you use a causal filter, you're going to be approximating this. So it's in fact, you won't be perfectly low-pass filtering. Those would, you would attenuate them, but they would not go to 0. Okay, if you use something finite. And you effectively are going to incur some delay, okay, if you want to make something causal. And this is actually what happens. Okay, you put the zeros, then you run it through some filter, which is finite, and you've got a delay. And if it's what's called linear phase, which we're going to learn later, what does that actually mean, then it's going to have a delay of half the filter length. Okay, so if you use a filter length of 128 samples, you're going to have a delay of 64 samples. Okay? Yes, that's a great question. It's a great question because it leads to the next slide. When you do something practical, okay, practically we cannot really upsample. Actually, upsampling and interpolation is exactly the same thing. Okay, interpolating is putting samples in between. Upsampling between samples you already have. Upsampling is really putting samples in between, right? Is making it higher rate. And that's exactly these are equivalent. So we can't really do a pure sync interpolation. We could do something that is approximate. Okay? And that's going to depend on the low-pass filter that you're going to be using. So if instead, for example, we use linear interpolation, whoever used linear interpolation in their life, raise their hand. Okay? Why do you use that? Who said easy? Yeah, it's super easy, right? First of all, has very minimum delay, if you think about it. I only need to know the 2 samples next to me, and I can find whatever in between, right? So the delay is very small. Okay? If you think about what it really is, it's a convolution with a triangular window, a continuous triangular window. And then you resample it. That's what linear interpolation is. Convolution with a triangular window. What is a triangular window? What is the Fourier transform of a triangular window? It's a low pass, right? It's sync square when we're talking about continuous time. But it's a periodic sync square if we talk about discrete time, right? So it is a low-pass filter, right? But it still has some sidebands. It's not a perfect low-pass filter. The bandpass is kind of has some tapering, right? So it's not constant over the bandpass, and it has some side lobes. Okay, so if we do sync interpolation, a linear interpolation, what effectively, if our spectrum looked like a triangle, then that would be effectively multiplying the low-pass filter, instead of being ideal, would look like a sync square, a periodic sync square. Okay? It would look like this. That would be the low-pass filter. And after the filtering, your spectrum is going to look like this. Kind of triangle, but it is actually a little bit slanted because the passband wasn't perfect. And there's going to be some side lobes. Okay? So those could be an issue. It doesn't give you an accurate representation. Okay? If I then, want to downsample it again with a half a sample delay, okay, like a one sample delay, then those things would then alias back. Okay? So if you think about this, there's issues by doing linear interpolation. You are, in fact, creating some aliasing or high frequency components when you do that. And again, it has to make sense because linear interpolation is piecewise constant lines. Piecewise constant, not piecewise constant. Piecewise linear lines which have edges, right? So they have to create high frequency. Does this make sense? All right. So this is the spectrum instead of having a triangle. That would be the ideal one. So we don't get effectively what we wanted, originally wanted. At the end, though, you have to realize what actually you want. If your signal is not band limited originally, that might actually be a better solution. Okay? So that depends. Okay, so then the real question is, okay, so you explained to me, Mickey, how to upsample by a factor of L. You explained to me how to downsample by a factor of L. But what if I want to resample by a factor of 3 divided by 11? Right? Or, some other rational numbers. What do I do then? And obviously it is possible because if I know how to upsample by a factor of something, I know how to downsample by a factor of something, I can now go to any rate that I want. Non-rational rate might be difficult using this way, but you can always approximate any non-rational number with a rational number. Right? So if you want to upsample by a factor of pi, your problem. Find the closest rational number. Okay? You'll be fine. Where this often happens, my computer, for example, plays something at 44.1 kilohertz. I play to you. You record it. Doesn't work. I recorded 45.1 kilohertz. I played on your machine. It plays slightly differently because yours, the clock is shifted by a little bit. If I want to do a high accuracy type of correlations of signals over a long time, that could be a problem. So you want to maybe resample and correct for these clocks. Okay, and this is one of the ways to do this. So I want to resample at from t to t times m over L. And the way I'm going to do it is I'm going to upsample by a factor of L and then downsample by a factor of m. Just concatenate those. Okay, so upsampling and then low-pass filtering by pi over L with a gain L. And then downsample, low-pass filter that by pi over m and then downsample. So this is the anti-aliasing filter and this is the post thing, the reconstruction filter. Obviously, you've got two low-pass filters. You don't have to use them both. You can just combine them to the minimum of pi over L and pi over m. Okay, and just use one. Now, what would happen if you flip them? You first downsample and then upsample. You'll still get the rate. But what would happen? You should not get any of this. Because before we downsample, we always filter. We always use anti-aliasing filter. We might lose some information, right? We might crop some high frequencies. Okay? So if we downsample first, let's say we want to let's say we went to resample at a rate of 1,000,001 divided by 1,000,000. And you downsampled first. You would get nothing. It would be a constant signal, almost. Okay. Obviously, that's not the right choice. Okay, so that's not a good idea. So how does it work? Let's pick L equal 2, M equal 3. We start with this. Now, if we do L equal 2 and M equal 3, okay, so it's resample by 3 over 2, right? Is that right? Yeah, 3 over 2. So we first sample, then we expand by 2. We low-pass filter by a factor of the minimum between pi over 3 and pi over 2. And then expand. Okay, and then downsample after that. That will give me this, which would have been the effective rate if I did a anti-aliasing filter plus sampling at that rate, okay, for this particular signal. Okay? And it kind of makes sense because if I start something that already occupies the thing and I want to go for a lower rate, I have to cut off some of those frequencies, okay? Because I cannot represent using so fewer samples that kind of significant bandwidth. So I have to get rid of some of the high frequencies in order to be able to do this. Okay? So now you know how to resample. What does it mean? And actually, if you look at the help of the resample function in MATLAB, there is an option to choose the filters for the upsampling. So there is a default filter, but it might not be good for your application. So pay attention when you do the resampling because it might not be a good choice. You might need longer filters, narrower filter, it depends, okay, for your particular application. Now, here's the problem, and I kind of raised it before. What if I want to resample by 1.01? And again, like the difference in the clocks between two computers, that could be really small. It can be like 1 ppm, 1 parts per million. Okay, it could be really, really small. The way I showed you right now, I would have to expand by a factor of 100. Lots of memory, big filters, and then downsample by a factor of 101. I put a lot of dollars here. It's not really the money, it's really the time. But time is money, so it's money. And money talks in America. So money is important. So that is an issue, right? Fortunately, people figure out a way around this because if you think about this, we're starting with a certain rate of signals, right? We're upsampling, we're computing a lot of stuff, and then we're downsampling. It's really similar to, how much work we need to go. If we just did the upsampling, we had to go to the continuous time, implement digital to analog, and then downsample. That seems like a lot of work to do, right? But we didn't really need this, right? Because we could do everything digitally. Now, if we want to go for that kind of rate, do we really need to go to almost analog and then downsample? No, maybe we can not compute what we shouldn't be computing. Obviously, if we're going to downsample afterwards, there's a lot of computation that we're not going to be using. Because we're upsampling and then downsampling. We're throwing away samples that we computed. So let's not compute those. If we don't compute those, it turns out that now the computation goes down. Especially in those situations. So, yeah, you could just concatenate trivially these operations, but if you actually think of what you're doing, first computing something and then downsampling, how about you just not compute what you're not going to save? Okay? And that's the idea. And the idea is to basically work in this multi-rate or what we're going to talk about is a polyphase decomposition of a filter. So if you want to do a filter operation and then downsample, or some upsampling operation with filtering, then there is a way to decompose this filter into something that will be very efficient, okay, that would not calculate those wasteful data because we're doing this upsampling and downsampling. So what we're going to do is we're going to use these compressors, expanders, and filtering, and we're going to interchange those. By interchanging things, for example, if I have a filtering and then downsampling, then think about it. I do the filtering on the high rate, and then I throw away a lot of the data. Okay. What if I first downsample and then filter? I should get aliasing, right? Maybe. We're going to come up with a way that you don't get this aliasing, but you could still interchange those operations. Okay? Okay, so how do you interchange operations? Expanders and compressors, they're not LTI. Okay? So if I have X of n goes to some filter, and then I'm going to upsample. Okay? If I interchange those, so I upsample first and then go to the same filter, this is not the same. Let's see how it looks. Okay? At this point, in the frequency domain, I've got x e to the j omega multiplied by h e to the j omega. Okay, in the frequency domain. After upsampling, I get a compression of both. Right? So both will be compressed by L. What happens here? I take x, I upsample, so now x is compressed. And now I filter with something that is not compressed. Okay? So this is not compressed, but this is compressed. So not the same thing. Okay? But I can change the filter such that it is equivalent to the filter that is expanded. Right? I could do that. So I can take x of n, upsample, and then not filter with h of z. We're going to filter with h of z to the power of L, which is a compressed version, compressed in the frequency domain, expanded in time, version of the filter. Okay? That will give me exactly the right thing. So I can exchange those, first do upsampling, then filtering, by taking my filter and compressing it, okay, in the frequency domain. This is a little bit unhelpful, though, because here I filtered on the low rate, then I upsampled. But instead, I'm going to go for upsampling and then filtering on the high rate, right? That's not a good idea. What I want to do really is the opposite. I want to take that and exchange. I want to take something like this and exchange them to this. And the real question is, can we move an expander from the left to the right with changing the transform? Okay. So my expander was here. That's a problem because I first expand and then filter on the high rate. I want to move it to here. So instead of now compressing, I'm going to expand it. Right? So divide by L instead of multiply by L. The exponent. Okay? Instead of multiplying by L, I divide it because it's the opposite. Instead of going that way, then that way. So can I do that? Can I? Can I? Yes? Always? Always? I can do that, obviously, because otherwise I wouldn't have talked about that. But not always. You can only do this if h of z is rational. Okay. Otherwise, that's not going to work. Okay? Here's an example, and here I'm going to finish today. Let's say I'm upsampling by a factor of 2, and I'm going to go through a filter 1 plus z minus 1. What is 1 plus z minus 1? It's a moving average of length 2, right? It's a moving average of length 2. The impulse response is 1, 1, and the rest is 0. Okay? So if I expand by a factor of 2, I get this. And after I do the moving average, I get a replication effectively, right? Now, if I wanted to then interchange the operation and move the filtering over here and the upsampling over here and change the filtering, right? Do a different filter. The problem is that this can never, never, ever be a result of an expander. Right? I cannot represent anything that will have an expander before that. Because it doesn't have zeros. So it's not a result of an expander. And because 1 plus z minus half, so divided by 2, is not rational, then that means that this can never be a result of an expander. Okay? Not a result of an expander, you cannot do this. However, here's a different case. Now, I upsample by a factor of 2, and now I have this filter, 1 plus z minus 2. Okay? 1 plus z minus 2, the result of that looks like this. It's kind of like a moving average, but it's not a moving average. It evaluates the value at the current position plus the value at 2 positions before. Okay? Not the previous one, one before that. Okay? So the result of this is always we'll have zeros after that. Now, this could be a result of an expander. In that case, I could flip them and effectively filter with 1 plus z minus 1 and then expand. Okay? What does it make sense? I mean, what are these values, right? What am I computing? I'm computing this plus this, right? And then this plus this, and then this plus this, and then this plus this, and this plus this, right? That's the result. So the value here is the value here plus 2 backwards. The value here is the value here plus this 0. So that gives you this one. The value here is this one plus this one. Okay? The value here, it's 0 plus 0. The value here, it's this one plus this one. I don't have to compute these zeros. What I could have done is just computed, take this plus whatever was before, take this and add, and take this and add, and skip the zeros. Okay? This is exactly what I'm doing. But what I'm going to do then is I'm going to throw away the zeros and then just do a moving average. There you go. Right? I don't have the zeros. And then afterwards, I upsample. So I do the moving average and then I upsample. Okay? Instead of doing summing the 2 samples before. It's doing exactly the same operations, but I'm not computing the 0 plus 0 now. I saved a lot of computation, twice. The computation by doing this. So the issue is that this is a problem, right? In these cases, for an arbitrary filter, right? That is a problem. However, as you will see next time, what I could do maybe is compute things on the even and use a filter, and then compute things on the odd and do a filter. But then I've got two sequences that are a result of an expander, because they will have zeros in between. It's just I'm going to separate into even and odd sequences. Maybe then I can save some operations. Okay? And so that we'll see next time, how to do this, and effectively not compute all the whatever we're going to be throwing away. Okay? So, with that, have a nice Wednesday, and I'll see you on Friday.